right, so I'm going to go over a little bit of the PowerPoint here, okay, about chemical reactions, because now that we have reviewed writing names, now that we have reviewed writing and translating word equations and vice versa, like the opposite way, we are going to go into identifying the different types of chemical reactions, okay? So there are 5 types of chemical reactions. There are more types in real life, okay, but most of them, like most chemical reactions that occur excuse me, can be categorized into these 5 types, okay. So I'll give you a quick overview and then we'll go into each reaction, and then we are going to dig deep into 2 of them, which is 4 and 5, later on in the unit, okay. So the first kind of chemical reaction is synthesis. To synthesize something is to make something. Synthesized music is music that has been made and modified. Synthetic diamonds are cubic zirconia, that man made diamonds. Okay? To make something is to synthesize something. So any reaction where you end up making a specific product is a synthesis reaction. Okay? Extremely commercially important, because most chemical reactions that happen have to do with making chemicals that we can use in our day-to-day lives and selling them and packaging them and marketing them. Okay, so synthesis is extremely important. So synthesizing is to make stuff. Okay, and the second type of chemical reaction is the opposite of synthesizing. So if synthesizing is making stuff, decomposition is breaking stuff down. You know this word from biology last year. If an organism is no longer alive, their body is decomposed by fungi and bacteria. Those are individual hundreds and hundreds of chemical reactions that are individually breaking down components that make up those living organisms. Okay, so everything can decompose. So decomposition is breaking stuff. You got making stuff, you got breaking stuff. And then the third kind is combustion. Combustion is literally burning something, okay. um your cars that you drive, I don't know, some of you can drive, some of you probably can't drive yet, but the cars that are driven around, they have combustion engines where gasoline is combusted to provide energy for the car to go from A to B, okay. But the reason that cars work on earth is because we have an atmosphere that is oxygen rich. We are currently standing and breathing and alive because we have oxygen to sustain us. And combustion also happens because there's oxygen. Combustion cannot happen if there is no oxygen. So if you took your car to a planet that has no atmospheric oxygen, your car wouldn't start, it wouldn't run, it would just be a piece of machinery that doesn't do anything. Okay? Combustion engines will not be valuable in an environment where there is no oxygen in the atmosphere. Okay? So that's the third kind. So we got making, breaking, burning, and then the last 2 are single replacement and double replacement reactions. Single replacement is you replace one thing. I'll show you what I mean by that. And double replacement is 2 different things get replaced. Okay? Now, let's talk about what synthesis really looks like. This red equation is the generic equation for synthesis, and the signature of synthesis is that it has one product. You got multiple components coming together. So A and B are the different components. You can have more than A and B. And A and B can either be elements or other compounds. They come together and they merge together to form one product. Okay? That is the signature of a synthesis reaction. So if I give you a giant list of reactions and I ask you, pick out all the ones that are synthesis, you can literally go down the list and select all the ones that have one product. Those would all be synthesis. Okay? So synthesis generic is A plus B react to produce AB. All right? Then the next one decomposition, but here are some synthesis examples. I forgot this was there. So this is good because these three examples show you compounds that are being combined. I'm going to remove this one because this one is actually forming an acid. And since I haven't taught you how to name acids, it's kind of confusing. But look at the second equation, okay? You got potassium oxide, K2O, reacting with H2O, which is water, to form potassium hydroxide, one product here, okay? And when I say one product, I don't mean numerically there's only one unit of KOH. It just means there's one type of product. Only potassium hydroxide is the end product. You can have any number as the coefficient. It could be 10 KOHs. Doesn't matter. It's just only KOH. There's nothing else forming. Only potassium hydroxide. Okay? These are compounds that are mixing to form another compound. And the third equation here, so this is 1, this is 2. The third equation here, these are elements mixing. You have sodium and chlorine mixing to form sodium chloride. You got sodium element, chlorine element forming sodium chloride, okay? But again, it's one type of product, all right? So it can be other compounds or elements that mix together to form one kind of product. And you can do this. So in the second equation, A contains potassium and oxygen, B contains hydrogen and oxygen, and they all combine together to form this compound, which contains potassium, oxygen, and hydrogen, all of the elements that came together. And then if you do it to this one too, you got sodium, you got chlorine, you got sodium and chlorine together, okay? So the generic reaction fits the actual reaction as well. All right. So if synthesis is making stuff and decomposition is the opposite of that, which is breaking stuff, the generic equation is literally the reverse of that. AB becoming A plus B, okay? That is the signature of decomposition, having only one reactant. There is only one reactant in decomposition. So in that list of equations I would give you, you would find the ones that only have one reactant, and they would all be decomposition. Okay? A and B is a compound. AB is a compound which is breaking into A plus B, and A plus B can either be elements or other compounds. Okay? There was an equation in your worksheet that we just looked at. It was this one, KClO3 potassium chlorate going into potassium chloride plus O2. So that's a decomposition reaction. You got one reactant, it's breaking into a compound and an element. So you can have any variation, okay? Here are some examples. First one is water splitting apart into H2 and O2. Second one is carbonic acid. This one is actually kind of cool, even though it contains acid, because you have experienced this one before. Do you guys remember your photosynthesis lab from bio last year? You had a blue solution, you blew into a straw, you turned the solution yellow. Do you remember that? Don't remember? Some of you should remember at least, right? When you had the blue solution that contained water, when you blew into the solution with your exhaled breath, what you were making was carbonic acid, H2CO3. So if I switch the arrow this way to make it a synthesis reaction, you are mixing carbon dioxide and water to form carbonic acid. And then when the solution turned blue again, this was what was happening. Carbonic acid was breaking apart into water and carbon dioxide, and the carbon dioxide was being absorbed by the plants. So your exhalation made a chemical reaction happen. Okay? Then the next one is calcium carbonate breaking into calcium oxide and carbon dioxide. Calcium carbonate, whoops, that's marble. Like the stuff that your countertops the bathrooms are made of. That's actual marble. You can decompose marble to form a gas, which is carbon dioxide that leaves the environment. This is why marble statues that are like in memorials and stuff, when rain falls on them, that rain contains acidic rain, which is like because of pollution and whatnot, literally makes the calcium carbonate decompose into carbon dioxide and calcium oxide. That's why you see all the pitting and the breaking of the marble. Okay? So, I also want to point out here carbonate is one of those ions that don't stay together as a unit on both sides of the reaction. Okay? Carbonate has broken apart on the product side, broken apart on the product side, which means when you are balancing it, you got to split about the carbon and oxygen and put it into your column. Okay? All right. Decomposition is done. Here is combustion. Like I said earlier, combustion requires oxygen in order to happen. Oxygen has to be a reactant in the equation by itself. That is the one rule for combustion. There is no generic equation, as you can see. But if the reaction has O2 in the reactant side, or the equation has O2 as a reactant, that is a combustion reaction. Okay? Here's one that you are familiar with. This is glucose. This is respiration. You're doing it right now. Every breath you exhale is evidence that this is going on inside your body. Okay, you got glucose from your lunch being combined with oxygen you're breathing in right now to produce water and carbon dioxide. This is a combustion reaction, except you're not burning from the inside, becoming one giant flame, because it's an extremely controlled combustion reaction where every single step, the energy from this combustion reaction is harnessed to make ATP and carried away by your body in terms of electrons, and then used to make ATP so you can sit and learn and function as a person. Okay? If every single glucose molecule in your body released all of its energy at the same time, okay, that would be a lot of thermal energy that would be released. That's a combustion reaction there, okay? So see over here how oxygen is a reactant in the equation alone. That is an indication that it's combustion, okay? Don't get confused if you're given a reaction like this, the one for carbonic acid that we just looked at. Some people think that because it's just a common misconception, because CO2 seems to contain the O2, that this is combustion. That is wrong. Okay? It has to be by itself, elemental oxygen alone, just O2, not connected to any other element. Okay? Lots of molecules have oxygen in them, but O2 has to be alone by itself for it to be combustion. Okay? So look at all these reactions. You got O2 here, by itself, by itself. These are all combustion reactions. Okay? First one, literally charcoal, carbon, burning to form carbon dioxide. The second one is methanol, that's wood alcohol, very toxic, forming or combusting to form carbon dioxide and water. And then the third one is magnesium metal, which can be burnt, combining with oxygen to form magnesium oxide. You have seen magnesium burn before, okay? Maybe not in school, but every time you light a sparkler, that white, bright sparkles, that comes from magnesium powder, okay? Fireworks that are producing very bright white light, that's magnesium powder. Question? Magnesium is not blue, it's white. I don't know what you saw, but it's not blue. All right, so I don't know what turns blue actually. I've never experienced a blue flame other than ethanol. So I don't know. All right. There's like lots of metals. I have not seen all of them burn, but 100% magnesium is white. Okay. All right. So we got three equations. I can find a video of magnesium because regularly, everyone, I feel very sad about this unit actually. You guys would all get to experience all the different types of chemical reactions in a lab form, okay? This year it's just going to be like videos, and you would actually get to burn your own piece of magnesium. It's like the last reaction that you get to learn how to turn on a Bunsen burner and then burn your own magnesium. It's extremely bright. It's like having your flash times 10. Okay. Um, but yeah, it's gonna just be videos this year. All right. So you got one, two, three reactions, but I want you to pay attention. These are all combustion, right? But I want you to pay attention to one and three here. Heat is not really like a product. Okay. So over here, I have CO2. That's the only product that has formed. One. One product. And magnesium oxide is also one product. So the type of reaction that gives us one product is synthesis. So some things that are combustion can also be synthesis, okay? Because burning something is a really good way to make something. Combustion is a way to synthesize some kind of product. So burning charcoal gives you carbon dioxide gas. Burning magnesium gives you magnesium oxide, which is used for different things, okay? So if you enter this situation where there's elemental oxygen in the reactant side, but you also have one product, you would write this reaction is a combustion slash synthesis reaction. Okay? Both things apply for that reaction. All right. One before last. For single replacement, I would be happy if you were noting some things down, honestly, because there's an equation here that is not on the slides. I'm going to write it out for you. So, whoops. So here are the two generic equations, okay? Single replacement, I don't know why this word is blue. Sometimes the formatting changes. But single replacement always has a special characteristic, which is it has one element that is free. So here's equation 1. A is the free element. And here's the generic equation 2. Y is the free element. So you always have a free element. And that free element replaces an element like itself that is stuck inside a compound. Okay? So let's talk about that in terms of the first equation. A is a metal. B is also a metal. A kicks out B to replace B and form a complex with X, making B the free element at the end. So at first, A was free, it kicked out B, it replaced B to form AX, and now B is free. Okay? So that is the generic form of a single replacement reaction. A plus BX goes to AX plus B. What was free goes into the compound. What was in the compound is now free. Now, the second version of this reaction happens to only 4 elements on the periodic table, and those are halogens. Fluorine, chlorine, bromine, and iodine in group 17 go through this kind of single replacement. Y is a halogen, it's the free halogen, and X is also a halogen. It's not B that's getting replaced, it's X. What did I write here? My bad. That's gotta be B. All right. It's not B that's getting replaced, it's X. Okay. So halogen Y kicks out halogen X. And now Y is in the compound and X is free. So Y was free before and X was trapped in the compound. Y kicked out X to form the compound By, and then now X is free. Okay? Same principle as the first kind. Just the element doing the kicking out is a halogen and the element getting replaced or kicked out is a halogen. So the free element can only replace a similar type element. Metal can only replace metal, halogens only replace halogens. Okay? We'll do more of these later. I'll come back to this. I'm not going to teach this right now. It's going to just be too confusing. So look at the first equation here. I'll actually show you a video of this first equation in a little bit. You got copper, that's the free element. And copper is a metal. Metals can only replace other metals. So silver is the other metal. Copper is going to kick out silver so that silver is now free. And copper is the one in the compound. Okay? So you have copper kicking out silver. Metal kicks out metal. So silver is free and copper is in the compound. Second one, same thing. Iron kicks out copper. Iron is now in the compound and copper is free. Iron was free first and then copper is free at the end of the reaction. If I write a version of this that is like in halogen, it will be Cl2 because chlorine is diatomic. Sodium iodide. So chlorine is my free halogen. This is free. Iodine is my other halogen. Chlorine is going to kick out iodine and form NaCl. Chlorine has taken iodine's place and now I have I2 and that's my free halogen. So chlorine was the free halogen, then it became trapped in the compound and now iodine is the free halogen. Okay? Balance this. Done. So that is single replacement. Last one, double replacement. Super easy actually. Double replacements are really easy. Double replacements are when there are two things that get replaced. So you got your generic equation, ax plus by go to ay plus bx. Here are the things you should note. A and B, both cations. That means they have a plus charge. It could be +1, +2, +3, whatever. X and Y are anions. If I put all of these in one big bucket and I shake it apart, okay, I shuffle it all together, right now A is paired with X and B is paired with Y, and I tell them you all have to find new partners, the only other partner A could go with is Y. Because plus and minus must go together. Plus and plus repel, minus minus repel, right? So the only other partner that A can form a compound with is Y. Because you need a plus charge and a minus charge. And B will end up pairing with X. So you got A going with Y. This is still plus. This is still plus. This is still minus. This is still minus. A with Y, B with X. the pluses and the minus just switch their partners. Okay, that's double replacement. Let's look at a example of this. You can actually write the generic equation right on top. Here's my plus, here's my minus, here's my plus, here's my minus. Plus and minus stick together, Ag and Cl forming this compound. Potassium and nitrate sit together forming this compound. Okay? Let's look at the next one. You got plus, minus, plus, minus. Na is going with Cl, plus and minus together. Potassium going with minus, plus and minus together. You have two compounds. This one plus, this one minus, this one plus, this one minus. Plus, minus, plus, minus. Okay? Literally, they're just switching their partners. So this one is super easy to do. Okay? Now, one thing that you should remember, I'm going to go back to this one, is that both of these, the reactants, are always aqueous. That's the state of matter for the reactants. They are solutions, okay? But the products can be anything. They can be aqueous, solid, liquid, or a gas. And I'm going to teach you how to identify what actually forms. Is it an aqueous compound? Are you going to see bubbling and form a gas? Are you going to see a solid, which is a precipitate? Are you going to form liquid water? That's something that you're going to learn at the end of this unit when we dig deep into double replacement. Okay? All right, so that's the end of the PowerPoint that I want to teach you. That's